I'm going to talk on some very new work. We've just, we've been working on the area for quite a while, for a decade, or no, 15 years or so. But just recently, some more work came up, and we're just filling in the gaps now. This is about the filling in the gaps work that we're doing. It's related to geospatial systems, and we didn't plan it, or I mean, I didn't plan it at least, but Serge has, if you like, set the scene rather nicely for what's going on. Unfortunately, I have a lot of slides, so I'm hoping that if I go through them very quickly, you'll get the right impression. I mean, I won't be able to focus on the details, so I hope you find them illuminating and confusing at speed. If it isn't illuminating, I apologise in advance. There are a number of themes. Yeah, okay, so Sergio pointed out in his presentation, if you like, the larger benefits. And I've been trying for a while, for some time, to characterise, or ways in which to characterise the benefits. And one of the ones that I'm becoming interested in at the moment is if you think of our computer ecosystem, it's got a structure, there's a data infrastructure in this computer ecosystem. So you can think of, the UK's got a critical infrastructure, electricity pipes and so forth, but it's also got a computer ecosystem which has got data, and this data is an infrastructure, much like the electric wires and the pipes that you see. And that, as with our critical infrastructure, some of it was bought, made a long time ago. We're looking through for the Roman sewer systems that are still running nowadays. So they built with previous technology, so you've got a chance, an opportunity to upgrade the infrastructure. And the idea is that the ontology is a tool to help you see the ways in which you can improve and upgrade the infrastructure, or even where you can see the flaws in the infrastructure, so where it needs to be upgraded. Choosing a particular example, serendipity, this is something that came up, Geospatial coordinate reference system. It's got a whole, there's an enormous, it's an enormous area of study. We've got to see this geospatial standards on the side. It has links into all sorts of different areas, but we're focusing on a core, which is just, if you like, what is a coordinate system? And when we dig down, it links into this bigger issue, which comes out, which is what a spatial object is. And hopefully, by the end, I'll be able to explain how it links in. And if we look at this, we look at the process whereby we start with the current state of geospatial coordinate systems, and we come up with a new picture. You can get some idea of the kind of ontological shifts that you can get if you apply ontology to data infrastructure. I'm going to spend a little bit of time framing the question, because I think the point of the example is to try and just get you to see a wider issue, so that will hopefully give you the context. Quickly look at the starting point, then do the shift, and then summarise at the end. So I think I sort of covered this a few seconds ago. Data infrastructure, the structures that underlie the computer data that we use. And there's all sorts of things you can comment on, but one big thing is that the structure can both inhibit and support more interoperability. Having the right infrastructure is quite critical to getting data interoperability. The other thing is that the actual infrastructure is often hidden. There's a famous essay by Susan Starr, The Ethnography of Infrastructure, which has a marvelous first sentence. This article is in a way a call to study boring things. And now I'm going to try and get a similarly interesting first sentence. But the point she makes is that no one looks at the infrastructure. It looks like dead. No one looks at it. When you start digging down, there's actually quite a lot of stuff there worth looking at. And the other point that Susan wasn't making, but I think it comes up with ours, is that when you look at the infrastructure, it's quite a lot of it's archaic and it needs to improve, and it's what's holding things back. And what I want to try and show today is that if you apply an ontological eye to this infrastructure, you can see ways of improving it. Serge mentioned before that the standard low thing is that ontology is a set of things whose existence is not by a particular theory. So what's interesting, and I think Serge said as well in his talk, is that when you try and work out, when you look at the data, you try and work out what the things are, after you start digging for a while, you realise it's not quite clear what things they are. So just the enterprise of trying to work out what things you're talking about requires a certain amount of effort. If you want to look at the infrastructure, so the broad patterns that underlie them, this again is a similar problem. One of the things we find is that using we need to look at the upper levels of the ontology, and if you have a top ontology, it's helpful to be able to surface the infrastructure, to surface the structure. And why is it important, in a sense, again, going back to Serge's talk, is that when you've got your ontology in place, this gives you a picture of the ideal or the conceptual infrastructure you're after. So it gives you a starting benchmark for, if you like, the kind of data structures you should be aiming for. It's an arts cartoon I think a lot of people use to illustrate what you're doing when you're doing ontologies. You know, you try to work out what things your theory is committing to. There's one aspect of ontologizing that comes out, again, if you go back to the philosophers, this quote here from Quine and Lewis, is that you start from your current conceptual scheme. It's not something when you start with a blank sheet of paper and you say, what's it going to be? You start from where you are and you build upon that and you clean it up. So it's kind of a, I think I'm trying to find the quote, it's kind of like a janitorial activity. You've got something, your job is to tidy it up. It's not to create something anew for something that through an act of creative genius, you find out what's going on. You start with what's there and your job is to tidy it up. Paradigm shifts are a useful way of characterizing this, because in a sense that's the way paradigm shifts work, is you start with the existing data and you look at it in a new way. There's a Kuhn appears again here. I think it's the same example that Sergio had, is this, whether it's a face or two vases, you can look at it two ways. When you look at the ontology, it's clear you've made a shift. There's no way that this picture on the left or this conceptual model on the left looks like the conceptual model on the right. You've plainly made a shift. And these kinds of shifts are, if you look at the history of science, are really commonplace. There's a Galilean relativity where he talks about a ship at a dock and someone in the ship dropping a ball and so forth. And Einsteinian relativity, I think, really has an embankment and a train going past how it goes. So they've got all of these different ways of looking at the same thing. One of the other things that was interesting I noticed in Kuhn is that he's saying, when do these shifts start? And it's quite interesting, he's got this notion of a crisis, but he says that what's intriguing is that people start trying to look at the different paradigms well before the crisis becomes emergent crisis. There's sort of unease and people start looking. And in a sense, I would argue that's where we are now. We've got some sort of unease, we realise the data's not quite right, so we're trying to look at the foundations to see where it's better. How am I doing for time? Okay. So, as indicated before, we're going to start with the current paradigm. We're going to try and surface the objects, so what objects are there? Then we're going to go through a series of steps, tidying these up. And we're going to do it in stages because the topic turns out to be quite technical. So I'll zoom through stuff. If you've got specific questions about the technical aspects, if you save them up, I'll answer them in the panel. Just two big things is that maybe just to help you see what's going on. There's two stages. One is physicalizing the coordinate system. So what's the physical reality? And then there's the next aspect is game setting, which is choices about how we represent it. So, Serge helpfully came down and found the coordinates of where we are now. And this is what came up on his phone. And you can see it here marked in Google Maps. It's got a coordinate. So one of the things that's interesting about the coordinate is that it's trying to give you a position that's the same today and tomorrow. It doesn't change over time. So it's time invariant. So the aspect, the key aspect of it is it's labeling something as the same It's going to be the same at different times. And I want to suggest that this, in a sense, is something that's spatial without being temporal. And this characterizes what being spatial is. Trying to work out the coordinate system is a amazing, well, it gets more and more sophisticated and intricate exercise in metrology. So we simplify it a little. You have your idea of a point, you take your point at different times, and you map it onto, typically into a geodesic data, which is a reference ellipsoid, and then you take a section of the surface of the ellipsoid and you turn it into a map, and you end up with this picture of the left. So there's a series of, there's a process of getting here, and this is how it's defined. So you have your time slicing, your data realization, and your map projection. You can do a model. It's probably easier to go back. Is that you can see there are these three general areas: features, space, and time, and geometry. And you can see them appearing in the sand. It's the same sort of picture appears again in all sorts of different places. It's probably easier to see it in this kind of Euler diagram where you abstract away from the conceptual model just the general picture. So you've got, when you start off, you have different objects for different purposes. You've got features for the various things that you have in the world. You have space and time for starting to divide things out, and then you map them onto mathematics, which give you your timeless spatial structure. Just to note, which is a point we'll come back to, is that because these domains are completely distinct, you've now got to explain how they relate to one another. And they certainly are not allowed to touch or overlap because they're such different domains, such different things. You can't, imagine a mathematical object like a number overlapping, I don't know, a particular table or chair or something. Okay, so we've mentioned that the two stages. We're going to try and first of all outline the physical basis, and then if we have time, we'll look at the gauge constraints, the different ways of representing it. Let's go on quite quickly. So the first thing that, the first step that we take is, where in the previous thing we're taking time slices, we take a leaf out of work that's done on relativity. We say that, look, if that point is traveling through space-time, it traces out a world line. So a natural maneuver, in fact, if you read any of the literature on relativity, so any time after about, I don't know, 1905, 1907, if you're in physics, the way in which you would trace a coordinate point is with a world line. This would be a natural way of doing it. And then you have a one-to-one mapping, if you're keeping this old infrastructure from that world line into your geodetic data, which then goes into the map, and you come back here. If we look at what's happened now, is that where in the past we had three domains, now we have two. There's been a unification on here. Worldlines and space-time universe and Earth all come together into one unified structure. And again, you can extend. You've got these issues about, you haven't got these issues about how they interrelate because it's a single domain and naturally interrelate in a usual way. The next question, the next thing we want to deal with, if you go back, is that how do we explain the relationship between the geometry objects and the features? And one of the things that, if you look at the geodesic literature, particularly the standards, is they start off with something that, if you're interested in the philosophy of mathematics, we call a Platonist ontology. They see the coordinates as something in a R2 space. That's a space of, they take two real numbers, ordered real numbers. And where the numbers are abstract objects, they're outside space and time. If you try and work out what's going on in terms of doing ontology, there would seem to be one R. Well, you have to worry about affine geometries and so forth, but let's just simplify one R2, one R3 space. There's only one coordinate there's this one coordinate here in the mathematics. But there's another way of doing it. There's another way of thinking about this, is you can say that R2 and R3 are a structure, and this particular attitude is known as structuralism, And you get various physical instances that are examples of this structure. So this gives you an opportunity for thinking about things in a different way. And if I'm lucky, the next slide will show it. Yeah, so what happens now is that let's say your coordinates here and your reference ellipsoid could be objects in the real world. And the reason that you can talk about R2 or R3 is because the structure, if you organize those objects in the right way, they've got an R2 or an R3 structure. So we physicalize, essentially you're physicalizing more and more of the original structure. And just a small thing you can see here is even the R2 structure then maps in there. You still get your physical mapping. So when you come back now, as if you do your Euler diagram, and you imagine the original picture where you had 3 boxes in 3 domains, you've now got 1 domain. We're now integrated into one single domain. Oh, okay, I'm getting faster than I thought. This bit of the story took me at least a while to make sure I got my head around it. So one of the issues you've got is different coordinate systems pick out, well, firstly, different coordinate systems share the same wordline points. And in fact, what happens if you go back to this picture here is that what you see when you go from R3 to R2 is that it's the same wordline is being shared in both of them. So they obviously share the same wordline points. But even quite different coordinate systems, provided they're set up in the same way, will have it. So for example, if you were to have roughly the same reference ellipsoid, but you might shrink it or expand it slightly, you would end up with different labelings on the coordinates, but you end up with the same word lines. The other issue is that different coordinate systems are different because they use different word lines. So how do we try and capture when a reference system is the same in the sense it's using the same word line and when it's different? And I think that's what we're trying to do here. So what we're trying to work out is when you create your geodetic reference frame, when you pick picks out these word lines, what is it that you're picking out? Let me just see where we are. Okay, so there is John Norton came up with this notion of relative space based on work of based on trying to explain what Einstein was trying to capture in his original idea. And the idea is that for every we've heard you've probably come across this before, any object moving through space-time takes with it its own inertial reference frame. And the idea here is that you can trace given the object, certainly for the object, you can trace its path through space-time, but you can also extend out world lines to the side so that you trace out the whole of that area of space-time. These came to be called in the literature time-like congruences, where a congruence is a series of world lines that do not intersect but cover the space-time, which, if you think about it, is actually the underlying structure behind the coordinate system. Because if you think of if two coordinates have got different numbers, they trace different paths through space-time, and none of the coordinates intersect. You find a coordinate system where, if you like, these two labels somehow came together and joined, would be an odd coordinate system. So in a sense, this is capturing the essence of the structure behind coordinate systems. And certainly, if you read the relativity literature, this is the way they think about them. And just to look ahead, as noted here, so being in the same spatial place means being on the same, staying on the same world line. So if you take this set of world lines, if you stay over time, if you stay in this place here, you're staying in the same place, but you're staying in the same place relative to these world lines, which is what happens on the next slide. So each of these, this is a Galilean relativity example we had earlier, has an example of a ship, and on the ship, someone drops a ball, and if you're on the ship and you look at it, it looks as if it goes straight down, but as the ship is moving, someone on the wharf would see it moving in a different direction. And it's got the idea of that because the ship is moving, this fish in the water might think it's staying still relative to the ship it's moving. So if you do this, create a relative space for these two objects, if you create a relative space for the ball here, which is going down, which is this thing here, and a relative space for the fish, is their world lines diverge? World frames, relative spaces. And depending on where you are, you can be at rest. So if you're in the water with a fish, you're on one of these world lines and you stay relatively at rest to it. If you're bouncing up and down with the ball, bouncing down or moving down with the ball, if you're staying relative to this, you'll be relatively at rest with the ball. Let's see. One of the interesting historical issues related to this is that most of the base work done for geodesy, in which most of the geospatial systems is done, seems to have been sorted out in the late 19th century, or across the 19th century. So it was all in place before the 20th century started, before Einstein does it works. And I think there's a kind of a siloing going on in the disciplines, is that basically the foundations have been agreed, the infrastructure had been agreed in the 19th century. So when Einstein's work came along, there was no real reason to update the way you think about relative spaces. That's not to say, of course, that the current geodesy doesn't worry about space-time curvature and stuff, which it needs to for doing things like satellites. In fact, it's very important to do it. But the thing that it doesn't take with it is, if you like, the philosophical baggage that Einstein brought in with relative spaces. Again, we have this sort of structure here. The difference here, now that we've got relative spaces, is that what we've got is world lines, if you like, defining all of the structures that we need for coordinate systems. I was trying to work out, my interest came in because I was trying to organise, trying to give a story, a narrative for this, which was consistent, but explain what the objects are, to pick up what the objects are, which is quite difficult in the original story. I was also trying to look at, if you like, the way it may impact on it. And I think one of the things you notice in the literature is they're quite clear is that they want to be able to measure mereotopological type relations between the objects. So they want to know whether the two objects overlap, where they touch each other, and so forth. In the literature, they have a series of systems for setting up mereotopological relations, and the literature says that these relations only hold within a mereotopological space. But I'm unable to find anywhere where they're quite clear, apart from saying in this particular coordinate system how they define the mereotopological space. So one of the things that is interesting is this notion of relative space. The Einstein-Norton notion of relative space actually gives you the definition of what your mereotopological space is, because up to the extent of the relative space, the relations hold. If you move into a different relative space, they stop holding. So this gives you a way, relative space gives you a way of looking at coordinate systems and seeing where they share the same physical basis, so it's the same sort of mereotopology. We looked at specific systems, and you can work out from the details in the system where they're saying. So if you go across these lines here, these coordinate system reference systems here share the same relative spaces. If you go down, they don't. And these things here, even within a particular way of building up your space, this would seem ITRF would be the, if you like, the ensemble where it comes from, is that these two are different because they've changed the basis of different relative space. So your mereotopological relations will no longer hold as you go from one to the other.
Chris, 5 minutes.
Sorry?
5.
Okay. All right, okay, and I'll zoom. So the next thing that comes out of it is that, again, this is another notion that comes from the work that's been done on relativity. It's the difference between, if you like, something that's physical and something that's a gauge freedom, which is the way in which you represent something. And it turns out that there's quite a bit of the coordinate reference system structure that is a gauge freedom. For coordinate systems, the metric is a gauge freedom. So in relativity, it's not, it's something physical they try and measure. But because of projections, because you can choose what metric you have with projection, because the projection changes the metric, it becomes a gauge feature rather than a physical feature. And there are things about the frame, so which axes you have, which order the axes are, and so forth, all gauge freedoms. Yes, this shows, if you like, you can visually see that you've got two maps with two different projections. If you apply, in fact, you do it on relative distances, you can see because you've projected, you can see the grid here is square, whereas the grid here is curved, you end up with a different metric in the two things. So, illustrating gauge freedom, it's not, this isn't quite right, but we see these different scale things can be a kind of gauge metric. This is coming back to this topological things. This is from one of the standards saying that this is the kind of thing that they want to measure. One of the things that I don't know whether I have time to explain it. So one of the things that's interesting is that you build up, once you've got your world lines, you build up spatial distances in terms of the world lines and world sheets. Whereas you'd because you need to have an explanation if you've got if your base is space-time and you want spatial distance, how do you get spatial distance? You get spatial distance by building it out of world lines to get world sheets. Okay, this is an example of, these are different choices, so depending on how you choose, so it's a gauge choice, how you choose what kind of axes you have, you end up with different number sets, you end up with different labels. So the actual label, the name you give to the point has a series of choices. You can do the same point will end up with very different numbers depending on which axiom scheme you choose. Again, you can cache out, because now if you go back to here, if you take this particular, say, R, you say, what does this R define? Actually, what it defines, I need to get it right, it defines one of these cones here. Yeah? And these cones are built out of world lines, and they're spatial, so they're time invariant within the coordinate system. Okay. So I was quite taken by these quines talking about smoothing kinks, lopping off vestigial growths, clearing ontological slums. Is a way of defining what happens when you apply your ontological gaze, as it were, to the topic. And I think hopefully you can see some of that as we compare the early story of what a coordinate system is with the later stories. You've got more structure, it's clearer what the objects are, and so forth. It's also clear, hopefully, that we've done a big shift. The other thing that we haven't spent much time on, but this idea is that the coordinate point is spatial within the whole coordinate reference frame. It seems to be true for other things. So you can do the same thing with, you take a centrifugal pump, you can take each of these, this is, if you like, a spatial breakdown of the pump. These objects here will be composed of world lines or world tubes, but it's only within a framework. So if I apply, I don't know, a breakdown from a table to a centrifugal pump, it won't work. So I need to have a spatial framework in order to get a spatial structure. A spatial structure is relative to a spatial framework. Just to reinforce the point that we've done a paradigm shift, if you look at where we started out with multiple objects, at the end, in a sense, you've got one object with multiple roles. You try to, if you like, capture in a simple way the difference of what's going on. The other thing is that if you stand far enough back, and I hinted at it, is that in the original picture, if you're looking for things that were distance invariant and maybe also topological invariance, it was just within the coordinate system. And it was a different one between R2 and R3, but you have a 3D relative space. same relative space can apply to both the 2D and the 3D structure. It can be the same relative space. And then the metrics tend to be different. I think you can probably gerrymander a case with use the same metric across the 2 and 3D, but typically they're difficult because the 2D metric is the surface of a reference ellipse sorting curve and so forth, so it's unlikely to be the same metric.
Chris, me too.
Okay, and I think I'm on my last slide. Okay, which I'll leave you to read. Okay, thanks.